Okay, so hi everybody. Welcome to today's session, and we're having Andrew here today again for the second part of dynamical code. And in the last session, we moved from the subsystem code to the dynamical code as a generalization. Just for example, the honeycomb code. So in today's session, Andrew will cover more detail on this part. So let me hand over to Andrew. Okay. Andrew, maybe you can unmute yourself. Sorry.
All right, can you hear me now?
Yeah, yeah, cool.
Awesome. Yeah, I'm just gonna continue on this dynamical code stuff from last time. Yeah, I'm just gonna first recap on like what I covered last time. And then yeah, I'm gonna go through some new stuff as well. Um, just do this. Um, Right. So first, yeah, I'm just gonna recap on like this, how you do like this stabilizer group update. So just by considering this example when you measure like this two Z's on top on this 412 surface code, then yeah, I'm not. So this is basically what I covered last week. So basically, like you're projecting your code state onto the the eigenstate corresponding to the outcome O of this measurement S prime. And basically, what you will find is that it's your new code state, this phi bar. It's gonna be stabilized by this three operators. So as you might see, like the first one here, this operator depends on this outcome O, which gonna be either +1 or -1. So after you measure this two Z's on this two top qubits, then you're gonna update your stabilizer from this stabilizer S to the stabilizer S prime. Yeah, and just to clarify, probably like some confusion from last week. So this new stabilizer S prime is going to be dependent on this outcome O, right? So this two operators now has like this dependencies on this outcome O. Um, oh, okay, yeah. Perhaps I should stop a little bit, see like anybody have any question on this part. Probably like something some carryover from last week. Um, yeah, okay. I'll just keep going. So yeah, I put down like this two exercises last week. Can you go back to like this S by measuring this? So yeah, so um indeed, you can. The reason why this XX on this two left qubits is because now like this this two stabilizers. I just use the pencil here. Like this guy and this guy is going to anti-commute with this S prime prime. Then if you do like just apply the update rules, then you're gonna combine this to one big 4 qubit C like this guy. And um like this one remains, and this is gonna be your new stabilizer, which is this one. And you can also get this by just multiplying this with this for weight for stabilizer. So yeah, it's just equivalent. Um, yeah, and on the second thing, like what if you measure this two z's on the bottom? Well, so that these two guys are going to anti-commute with that, and then just do the same stabilizer update. So you're gonna end up with the same stabilizer S prime. And yeah, I kind of like omit like, so there should be like some outcome O there on these two guys as well. But yeah, I'm just like for simplicity, I assume that everything like the measurement outcomes are +1 because in practice like they're gonna be completely random. Um, yeah, and also like um, so there's this exercise from last week. So what if we think of this two stabilizers as a gauge as a subsystem code? So the gauge group is just the union of this um as this group generated by the union of these two stabilizers. And then you can write it this way. So I just take the generators from S and S prime. This guys, I should delete that. Um, and put those generators together. So now I have six generators, but some of them are redundant because I can generate this last bit by multiplying this one and this one. Same thing with this. I can multiply this with that, and then I get that one. So I can just get rid of this too. Um, so now I have this four um, um, gauge operators, right? And why I call them gauge operators because these two are anti-commute. Um, but yeah, the first two here, they commute with each other. Um, so if you recall like this partitions of your physical qubits or data qubits into like stabilizers and gauge qubits and logical qubits, then this is kind of like what you're going to get. Um, so this first two that commute with everything are basically going to be the stabilizers, right? So those are this Z1 bar and Z2 bar. Um, and so yeah, they commute with everything else in G. So they're in the centralizer of G. Um, so they're going to be our stabilizers. Um, and yeah, so these two are going to be the gauge um, operator, X and Z gauge operators corresponding to one gauge qubit. So this Q of G, like this defined by this gauge group, is this 4112 subsystem code, which means we have four data qubits, one logical qubit, one gauge qubit, and distance two. Um, and then yeah, we measure that. We measure this x3, which is this guy. So that's going to give you the state in this first stabilizer group S. But if I measure Z3, like this guy, then I'm gonna get this I'm gonna update or like kind of like get this stabilizer group S prime. So this is kind of like the thing that's called gauge fixing, which I believe Derek has covered in his one of his tutorials. Yeah, and up to some measurement outcomes. Yeah, just omit them here. Um, right, yeah. So we basically like we have like this kind of like diagram. So from this gauge group corresponding to that 4112 subsystem code, um, so if I measure like this guy, I'm gonna go that way, and I'm gonna get this stabilizer group. If I measure this, I'm gonna go that way, and I'm gonna get this stabilizer group S prime. And then like once I go to either of them, I can go back and forth between them, right? By measuring either this two Z's on top or like two X's on the left. Um yeah, as we have discussed from last time. And like yeah, like so actually like the logical operators stay the same. So we have like this X logical operator corresponding to this two qubits on top. So this is X bar, and there's two Z's on the left. That's Z bar, and they're the same for all of these codes. Um, yeah, so these are like how you update the logical operator. Just a quick reminder. Um, so in our case here, so this logical operator they commute with if I measure this S prime, they commute with that. Um, and they commute with this Z logical as well. So both logical operators remain the same, and that's the reason why we have the same logical operators. Um, Yeah, so just I'm gonna flash out like this stabilizer update rule. I'm probably just gonna so basically like the principle here is basically like you measure something and you take out just you come up with some generator such that only one of the generator element of the generators commute anti-commute with your measurements, and then just get rid of that and put in your the measurement yeah, your measurement basically. So that's this last rule. But yeah, so the second rule, you're basically doing logical measurement. And then the first one, your measurement is in the stabilizer, so it's a stabilizer measurement. Stabilizer. Yeah, so yeah, that's basically the principle here. Like this last rule is probably like the most important thing to understand. Um, yeah, and the logical update rule, um, yeah, so if your measurement is equal to some logical operator, then you're doing logical measurement. So now your logical operator becomes a stabilizer, and that's generally not good unless you want to kind of like actually do a logical measurement in like some computation. Um, yeah, and this case is what we've seen in that 4-qubit surface code example. Your logical operator stays the same. And these two cases, when your measurement does not commute with L, um, yeah, so like in this third case, commutes with all the stabilizers. So now that means that, but it anti-commute with some logical operator. That means you kind of like do like this gauge fixing thing because you kind of like measuring some logical operator that's anti-commute with this L. So it's kind of like if this L is an X bar, then this L prime that anti-commute with it gonna be like this Z bar corresponding to that um X bar um qubit, that the same qubit logical qubit with that X bar. Yeah, and the last thing here is when it your P does not commute with this L and also some stabilizer of S, then you do this kind of update using this G1 that you remove from that last rule in the stabilizer update rules. Um, yeah, and this is the honeycomb Floquet code, which yeah, I'm not gonna go into super detail here, but essentially here, like like you cycle between this three stabilizer group. Oh, sorry, so this should be like S1 and S2. But yeah, anyway, yeah, as you measure like the this green checks, and then you measure all the red checks, and then you measure all the blue checks. Yeah, so this is the code that I did not really didn't have the chance to go into last time, so I'm just gonna spend a little time on this. So yeah, so this ladder Floquet code is basically so you have this kind of like ladder shaped lattice. So this kind of like wraps back around. So this qubit is the same as the qubit there in those two. So this kind of like cycles back to that part. Um, right. So what are the measurements here? So the measurements are, so we have this ZZ measurement on the this vertical edges, and then like on the horizontal edges we have either YY or XX measurements. So the measurement schedule for this Floquet code is that you measure ZZ and you measure all the XX and you measure the ZZ again. But after that you measure all the YY checks, and then you measure ZZ. And then you keep repeating that, right? So you're basically alternating like this X and Y measurements. And then between those, you put in like the CZ measurements. And what that does is basically because like after I measure all this ZZ, then I measure the XX. So this check measurements are gonna anti-commute with that, and also anti-commute with that. Um, and then what that means is that now I'm measuring yeah, I'm gonna get like this for oh okay, I'm using red on red. So let me change color there. So I'm gonna get like this ZZ, right? And I have all this four Z's on the red plaquettes. Um, and now yeah, what I'm going to so what I measured here is essentially a stabilizer in this red plaquette. And what that stabilizer is basically the product between like this ZZ and XX. So this plaquette is going to be actually a YY stabilizer. Um, so that's the kind of like the syndrome that I get, right? So I'm taking the product between like this two ZZ measurements and the two XX measurements corresponding to the edges of this square, red square. And I'm gonna basically measure this stabilizer. Um, yeah, and then if I measure like the ZZs again, after I measure the XX, I'm gonna measure like the same thing, right? Because I'm taking the parity between the outcomes of this XX and ZZs. Um, now once I after that I measured YYs, which are gonna be like this guys. And now I'm gonna get this ZZ again. But actually like the stabilizer on this green plaquettes are gonna be the product between the ZZ and YY, so it's gonna be a XXXX stabilizer. Okay, then I'm just gonna keep doing that, right? So that's basically how this works. But yeah, so regarding the logical operators, sorry, I don't have it typed down here, but oh, I don't want to. I just want to switch to new color. Um, so you're gonna have like this one loop logical operator that kind of wraps around like this ladder plaquette. Um, but the other logical operators that's gonna be something that goes vertically. Um, so that makes the distance of this code two, which means it's only kind of like error detecting, but yeah, and not error correcting in the worst case. But yeah, but that's still a dynamical code, um, which is kind of cool because you only need to do like this bunch of 2-qubit measurements. Um, okay, so now I'm gonna shift to this Bacon-Shor code, which I believe Derek has covered. So I'm just gonna do like a little recap here. So how this Bacon-Shor code is defined. They're defined by 2-qubit checks. Um, and the checks are gonna be on the edges of this lattice. So the red edges corresponding to XX measurement. Let me write that down. X X. And then the blue edges are going to be ZZ measurement. It's blue. Yeah, so that's generates the gauge group, right? So this is what this basically means. And yeah, you can see this is not a subspace code because like this XX is going to anti-commute with this ZZ check and that one as well. Um, so we can think of the Bacon-Shor code as kind of like a dynamical code because when you do like error correction in practice, you cannot measure all this X and Z checks simultaneously. So if I measure all the X checks and then the Z checks, and keep doing that alternately, then I'm going to kind of like switch between two stabilizer codes. Okay, if I just start from like I have like this gauge group, then I measure all the X checks, um, then I'm gonna end up in this instantaneous stabilizer group. Um, and basically what this means is that so I have like all this X checks, right? So all this red edges in my stabilizer group, this CX. Um, but then what it does is that if we use our stabilizer update rule, then that's going to kind of you have to take the product between this um, um, two Z checks. If I measure this top red check, and then I keep doing that for the next one. If I measure this one, um, and then what we're gonna end up is a product of this one row. So that's basically what this guy is. Um, yeah, but okay, so that's what I did. First, I measure all the X checks. Then what happens if I measure all the Z checks? Um, then if I measure this Z checks, then that anti-commutes with those two. So now I have this like this 4-qubit X check. And then I measure that or um yeah, I measure like this Z checks, like this two. Then I'm gonna combine this all this X stabilizers, and then like just keep iterating the update rule. Then you're gonna end up with this column of X's, and that's gonna be the this X stabilizer. So yeah, if I just alternately measuring X and Z, I'm gonna alternate between this instantaneous stabilizer group S0 and S1. Um, and kind of like the reason why the Bacon-Shor code has this two logical operators. So a an X logical operator here. So that's X bar, and then I'm gonna have like this Z bar. Change that to blue. It's the reason that we have that is because I kind of like never measure that in this measurement sequence, right? Because I'm measuring all the z's vertically and I'm measuring all the x checks this that goes horizontally. So this two kind of like string operator are never measured. Um, Therefore like they're in the normalizer. You see, if you can see like this sort of commute with all the checks, um but they're not stabilizers because we never measure them. Yeah, I'm just gonna just gonna define some convention on how to like define. I believe this is also covered by Derek in his um, tutorial. So we can define a gauge qubit on each square in this lattice this way. So this is going to be the X gauge operator. This is going to be the Z gauge operator, and they're going to be just like the Z's on the vertices of this blue boxes, and the X are going to be like X's on the vertices of this red boxes, right? And they coincide at this one vertex, so they anti-commute, and they're going to be constitute like virtual X and Z for this um, logical gauge qubit. Yeah, and the stabilizers, you can define them as rows and columns, as we've covered in the last slide, and the logicals are this, right? So you can identify this with some kind of like this imaginary square outside, right outside the lattice. The same goes with the logical operator. Um, cool. I'm gonna stop real quick if there's any question. Okay. Right. So I'm not gonna go to this dynamical Bacon-Shor code in more detail. I believe Derek also mentioned this at some point in his talk. But yeah, I'm gonna kind of like cover like how you do the updates and stuff here. Yeah. So your measurement sequence here are basically all the red edges corresponding to qubit X checks, except on this column where we have like this A and D squares, and we denote that by this, right? And in the next round, I'm going to do like this Z checks on this blue edges, except those in this AB row, and that's this second thing, right? And then like the third and the fourth check measurements, they're defined similarly, right? But we just shifting this rows and columns where we don't measure the checks except for one in the middle. Um, so what that gonna give us is that now we're gonna have like the stabilizers are going to change as we gonna see. I think I'm gonna do that in the next slide. Um, and the logical operators, you're gonna have an extra logical operator basically, and that's going to be represented by this red line. So that's kind of like the dynamical X operator. Oops, um, go back. Yeah, so this red red two red lines. So this is kind of like logical X, and this is the logical Z. And then if I do like this measurement, second check measurement, then it's going to change. So it's going to shift to like this to this form, and it's going to keep changing. And we'll see in the next slide why this how the stabilizers and logic operators change. Um, right. So okay. So let's just look at this very first measurement round. So we still have like all the stabilizers from the original Bacon-Shor code. And those will be like this Z's on the rows, right? And the X on the columns. It's red. Um, because you see like this gonna commute with any of like all the checks regardless, right? In any round. So you're gonna always have that, right? So that's this first thing, this S sub BS, right? So those are the original stabilizers from the stabilized from the original Bacon-Shor code. Um, and then you're also going to have the checks that generates the ISG. And then like what you're going to get in addition is that now you're going to get this the gauge operators um, that you kind of fix in this measurement round. And yeah, so okay, so how this works is that now I'm gonna have like if I go back to that slide because yeah, I can define like the gauge operators this way. So I associate each square with this two um gauge operators, right? So I'm gonna do the same thing here. Um uh, yeah, I'm gonna do the same thing here. So now I'm gonna get this logical Z logical operators in that column AD, except the ones in this row A and D. So I'm gonna get like this Z logical Z stabilizer, sorry, Z stabilizer, and Z stabilizer. So that's basically what this first bit means, right? And if you see here, so that is there because you kind of get that by from taking the product of these guys. Um yeah. And yeah, you don't extend it to this square because now you don't have like this x checks on that part of the this AD row. And I also have like this I also fix this x gauges in this column AD. Um so I'm gonna have change color there. Um this x gauge, this x gauge, um except for the one in this D, right? Because you remember like how we define this logical operator is that x gauge operator is that it goes like this, it goes vertically. um yeah, so I don't get the one from that emits from this um D square. But I'm gonna get the one from this one, that one. Um, yeah, and yeah. So basically, like these are defined similarly to the other ones. Um, um, you're gonna take like so in this ISG, so you're gonna have kind of like this X stabilizers. Okay, I don't think you're gonna, not that one. Um, so this one's right because you kind of like get that from these rows where you have like this X checks from the previous round. Um, yeah, and then you're gonna have like the Z gauge operators in your stabilizer group, which goes horizontally. So it's gonna be that that one, and you don't get this one because you're yeah, and those ones. Um yeah, so basically if if we just now if we count the number of logical of stabilizers, of stabilizer generators, um then yeah, we can basically see that so if I take like L and M as the so L is the okay, what is L here? Z10 L, so we go yeah. So L is the x-axis. So so this is L and this is M. So L by M, general L by M lattice. So in the original Bacon-Shor code, so these are the stabilizers from the Bacon-Shor code. So you're gonna have L minus one plus M minus one, right? Because now I'm gonna yeah, I'm only taking those on like the rows for the Z stabilizers, and for the X stabilizers, I'm going to take the columns. So I'm gonna have like L plus one, L minus one plus M minus one. And I also have like this one defect check, right? Like this thing in the middle that I measure in this kind of like weird column and rows. So that's going to be one. And then I'm gonna have like this gauge qubits that I fixed. Um, and that's gonna be this, and that's because I'm gonna get like all these so basically I can just count the number of squares where I have like these um logical where I fix this x and z or x or z gauges, and then I'm gonna get that. And I'm still gonna have like this original logical qubit, which are gonna be this guy and this guy. That's it's Z bar and that's X bar. So that's gonna be one, but we're gonna have like one left, right? So we just add this add all of this, right? So the defect check is one, logical qubit is one. So now I'm gonna have like this um yeah, so it's gonna be wait, cancel um L minus one plus M minus one. So this is gonna be LM minus M minus L. Um yeah, and then you're gonna get like one dynamical logical qubit. Um sorry, yeah, this is weird. So what's this? LM minus M minus L minus M. Hmm. Minus L minus M. Well, I'm gonna get plus one, right? So the two gonna cancel out. If I consider those two. And this is basically, so I'm gonna pull the L out. So this is equal to L um M minus one um plus or sorry. So minus M minus one, right? So I'm gonna get L minus one plus M minus one. Um minus one. Oh, I'm gonna get the same thing. Let's see. Um, yeah, sorry. I think there's like an some mistake here. Yeah, let me go get back to that. Yeah, and I'll correct it. I'll post something in the Discord. But yeah. Oh, okay. So it's gonna be the next part. Yeah. Okay. Let's just continue to this. Um, So yeah, so the next thing I'm just gonna talk about like how error propagates and how that might be useful and like analyzing on how you measure stuff in the circuit, whether you can detect an error or not. And to do that, first I'm gonna go cover this Clifford unitaries. Um, so a Clifford unitary, n-qubit Clifford unitary is basically defined by this. So if I take any n-qubit Pauli P and I conjugate that with UU dagger, and then it's gonna be another n-qubit Pauli, right? So it's gonna map you back to this set of n-qubit Paulis. So these are just commonly considered Clifford gates. So this is a C0 gate, so that basically flips the second qubit condition on whether you have 0 or 1 in the first register, and the Hadamard gate control Z, and the S gate or phase gate. Um, so basically like this conjugation, so that kind of like defines how what you get by propagating your Pauli through a Clifford unitary. So this is the propagation, right? So if U's are Pauli, then this Q is going to be, sorry, if the U's are Clifford and then this and the P is a Pauli, then the Q is going to be a Pauli, right? And if I just move this U dagger to the other side by multiplying U from the right on both sides, then I'm going to get this UP equals to QU, which means I can propagate this P to the other side, and that's going to change to Q. Um, yeah, so these are some propagations on like the gates that I've showed you in the previous slide. So if I put X into a Hadamard, I can propagate that and get a Z. But if I put a Z, then I'm gonna get out an X basically. Um, well, I can propagate it and it becomes an X. And an S gate, I put an X, gonna get y on the other side. But since it's a diagonal gate, if I put a z, I'm gonna just get a z because they commute. So for C nuts, if I put X on the top on this control register, I'm gonna get this XX, and that's what could be what could be bad in a circuit because now you have like this one error is equivalent to this two errors on the other side of the C nut. Um, yeah, but the X's commute with this C naught gate if it's in the control or target register. Um, and this Z commutes if it's on the um, control register, but the Z propagates to like this 2 qubits if it's um, on this target register. And then like yeah, it's gonna there's same kind of rules on this CZs. So the ones that propagates are this axis because this CZ gate is diagonal, right? If I go to like previous slide, right? Everything's on the diagonal um, in the Z basis. So the Z's just commute. Oh, sorry. So that Z should be on that qubit, not that one. So this one's identity. Yeah, but the X propagates. Yeah, so it becomes like this two Paulis. Um, so yeah, if we just look at like this simple circuit, right? So if I have like this X error here between, so this M's this denotes measurement. So this MXX is a 2 qubit measurement on this 2 qubits, and this MXZ is some 2 qubit measurement. So X is on the top register. Um, yeah, so say I have like this X error there, then I'm just gonna use this rule here for the Hadamard, so I can move that so that's equivalent to having like this Z error there. And for the C naught here, if I have this two Z errors, that's equivalent to just having this one qubit Z error there. Um, yeah, so okay, so if we look at the circuit now, I can also take the operators of my measurement and put that kind of like in this locations in the circuit. So if I do an XX measurement, I'm gonna put like an XX on like this two locations before I do the measurement, and do the same thing with Z and with these measurements as well. Yeah, so that's kind of like what happens here. Um, and then I can back propagate all these measurements, right? Or sorry, all these Paulis. Um, so like propagating this to x's is going to give me an x there, right? So that's why there's nothing there, but now there's an x there. And now I have this 2x and z here. I can further back propagate that there. So that cancels out this xz, this first xz. So now I have nothing here. Now just some identities. Um, and basically by doing like this propagation on this circuit with measurements, we can kind of like determine on yeah, so this is basically what we had in the last slide, right? So we have like those xx on this 2 qubits and x and z on that 2 qubits. We can kind of like determine whether an error can be detected or not. Oops. Um, so say I have like that z error there. So that can be detected because this z anti-commutes with this x here, right? So the same thing if I have like a z error there, or if I have like a single qubit x error there. Um, yeah, and this is why so yeah, I'm not gonna go into too much detail. So this is just kind of like this is kind of like a bit anticlimactic, but basically like there's a nice formulation called the space. time code where you can basically determine which error can be detected or not by doing this propagation. Um, yeah, probably can cover that in the fault tolerance session later on. Yeah, that's pretty much it. Thanks.
Okay, thank you, Andrew. Anybody has any questions here? You can either unmute yourself or just type in the chat box. Okay, cool. Okay, thank you, Andrew. It's a fantastic talk here.
All right.
Yeah,
Thanks.
yeah,
Yeah,
yeah.
I'll
Thank
put
you,
an
Kev.
update about like that one
Doesn't
mistake
matter. Yeah,
on the thing.
yeah. You can upload that
Yeah,
one
I'll post
to
something in
Discord.
the
Yeah.
I'll post something in Discord, yeah.
Okay.